All right, welcome back to physics, everybody. Today's lesson is on acceleration. We talked a little bit last week about what acceleration actually means, and just as a reminder, acceleration is the rate of speeding up or slowing down. So it's how much your speed is changing, or it's the change in your velocity over a specific amount of time. If we were to write that as an equation, we have acceleration is equal to a change in velocity over a change in time. And just as, again, as a reminder, just velocity is a change in distance over change in time. So this is not the same thing as saying acceleration is equal to the change in distance over change in time divided by change in time. We cannot just plug in this equation into this. It doesn't work. Okay, because this is just a single velocity, and this is the change in velocity. Our second equation only tells us about a singular point in time for velocity. Acceleration tells us how that velocity is changing. Now, if we only have a single velocity, then the acceleration would be 0, because there's no change in the velocity. However, if you're, say, in a car and you slam on the brakes, well, then your velocity is changing, and just the change in distance over time isn't enough to tell you exactly what's going on. It might tell you the average velocity over the entire time interval, but it doesn't tell you the whole situation. Let's go ahead and look at an example of this. Roger Rabbit slams on the brakes of his car. After 0.75 seconds, the car has slowed from 100 meters per second to 25 meters per second. What is his acceleration? In this case, if we need a visual, over some distance, we went from 100 meters per second to 25 meters per second in the same vehicle. Now, we don't know the distance, nor do we even care about the distance according to the problem. However, we know that there was still some distance covered. Our first step, as always, is to write our knowns. Let's go ahead and highlight all the numbers within the problem. There's 0.75 seconds, 100 meters per second, and 25 meters per second. We are looking for acceleration. Now, what are these different variables? That's our first question, of course. 0.75 seconds. Seconds is a measure of time. So our change in time is 0.75 seconds. We have two different velocities, and the reason that we know that these are velocities is because the units are given in meters per second. Meters per second is always a unit of velocity because it's a distance divided by a time. Now, we have two different velocities here, which means we need to figure out which one's the starting velocity and which one's the final velocity. What a lot of students like to do is try to make the smallest number the initial velocity, because that's just what's ingrained in them. They always want the smaller number to come first. It's not true, though. Negatives are going to pop up, okay? In this case, our initial velocity, v with a sub I, would be 100 meters per second because it says he slowed from 100 meters per second to 25 meters per second. Therefore, our starting velocity is 100 meters per second, and our final velocity, v with a sub f, is 25 meters per second. We are looking for acceleration. I'm just going to put a equals question mark. Our next step is going to be write the equation without substituting anything in. Acceleration is equal to the change in velocity over the change in time. The delta symbol, again, just means change in. If we rewrite this, and I'll only rewrite the top since we know the delta t, vf minus vi divided by the change in time. It's always, 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 always the final minus the initial, never the other way around. Okay, whenever you're writing this, that delta always means final minus initial, or final minus starting, same thing. Now, we are looking for acceleration, so we do not need to rearrange this equation. Vf is 25, Vi is 100, and delta t is 0.75. 25 minus 100 is negative 75. We divide that by 0.75, and we get negative 100. Now again, if you're not sure what your units are supposed to be, we can go ahead and put in our substitute in our units, just like we did the numbers. Velocity was measured in meters per second, and time was measured in seconds. Another way to write this is meters per second times 1 over seconds. All I did is rearrange it a little bit so it's easier to see. That gives us units of meters per second squared. Seconds times seconds, seconds squared. And that's your final answer. Example 2 says, Newton watches an apple fall from a tree. If it takes 2.8 seconds to reach the ground, what was its final velocity before impact? In this case, we are not solving for acceleration. We are still going to use our knowledge of acceleration to solve, however. First things first, write our knowns. We're going to go ahead and highlight any numbers within the problem. And in this case, there is only one number. Let's go ahead and put that in our knowns before we talk about the next bit. 2.18 seconds is a measure of time. And that's all we know right now. We do know that we're solving for a final velocity, because the problem does tell us this as well. So I'm going to go ahead and put in my knowns, final velocity equals question mark. Now, what else can we use to solve this problem? It says that we're watching the apple fall from the tree. Since the apple is falling, that means it's moving in a vertical direction and only gravity is affecting it. One thing that we always know about gravity, and I'm just going to expect you to remember this number, okay? It's in our notes if you need to ever reference it, but we're going to use it all the time and it's going to be ingrained in your memory. The acceleration due to gravity, so acceleration because of gravity, we just call g. It gets its own special variable because it's used all the time, and it's equal to 9.81 meters per second squared. Now, if you ever look at this and you just can't quite remember what it means, you can also rewrite it as acceleration with a sub g, acceleration with gravity. It's up to you. Just know I will always just write the letter g because that's the standard, okay? The other thing that we know is that the apple was in the tree to begin with, so we can assume that the initial velocity would just be 0, which means we are really looking for the overall change in velocity, just to make things a little bit simpler. Now that we have all of our different variables that we need, we're going to go ahead and rewrite our equation. Again, without numbers. Acceleration is equal to the change in velocity over the change in time. Now, we are looking for the change in velocity in this case. Therefore, we need to rearrange it for the delta v. I'm going to take, since I want that delta v by itself, I'm going to take that delta t and multiply it to the other side. That gives us a delta t equals delta v. Now that we have it rearranged for delta v, we can plug in our numbers. Delta v is equal to, now again, acceleration in this case is this g. We're going to go ahead and plug that in for the a here, since they are the same variable. They're both accelerations. we have 9.81 times that delta t, 2.18. That gives us delta V equals 21.4. And again, we don't know what our units necessarily are going to be. We can go ahead and plug in our units just like we did our numbers. Acceleration is meters per second squared, and that's multiplied by a seconds. One of the seconds cancels out, and we have just meters per second. And that's your final answer. Alright, again, guys, if you have questions, please email me with your questions. That's all.